All right. So thanks for coming back for session 3. Okay, so I just wanted to give a few brief sort of housekeeping things before we get started. So for those of us joining us remotely, remember you can join us by chat. We'll be monitoring the chat window. And we'll also take questions afterwards by email or Twitter. Okay, so basically in sessions 1 and 2, we've sort of covered this pipeline. So we started out talking about scanning and lesion drawing. We spent a good bit of time last week talking about running the lesion symptom mapping analysis, and then a little bit about post-processing. So you're probably wondering what's left. So we're basically going to sort of unpack the SVR-LSM analysis a bit more today, sort of take a more critical look at it and show you some of the kind of weird things that we've been seeing as we've been running this analysis. We're also going to touch on a alternative that's out there in the literature, which is known as SCAN, or Sparse Canonical Correlation Analysis for Neuroimaging. And then we are going to then introduce a sort of interesting novel approach that we've sort of been pioneering here at MRI. So normally at this point I turn it over to Harrison, but he is unfortunately not here today, so you're stuck with me. All right, and so just sort of a caveat, Harrison is really the one that has run a lot of these analyses. So I will try to answer questions if you have them, but I may have to defer to Harrison to address them later, or Frank might be able to answer them as well.
We'll try.
Okay. So, so we talked about VLSM first, or voxel-based lesion symptom mapping. And the idea there, as you remember, is that you basically look at a single voxel at a time. You perform some kind of test, like a t-test. And this is kind of problematic because it leaves us with a large number of tests that are sort of incorrectly assumed to be independent. Okay? So we wanted to turn to some kind of multivariate approach to get around some of these issues. And the one that's sort of most prominently out there in the literature, and that what we've used most often, is SVR-LSM, or support vector regression lesion symptom mapping. And so there we perform a single multivariate test, which gives us a map describing essentially all of the voxels in the brain at one time. But the downside, of course, as we talked about last week, is that if you now want to interpret the map that you get back, you have to do this by sort of running permutation tests and then going in and looking voxel by voxel. And so this means that you're still looking at the voxel level. And so there is some uncertainty about what to do about multiple comparisons corrections, because now this is no longer clearly a large number of individual tests, and it's no longer a single test across all these voxels. It's sort of this weird hybrid mix of the two. And then we also don't quite know exactly how to correct for lesion volume, and I'll touch on that a little bit more in the next few slides. So in terms of correcting for lesion volume, the reason why we really want to do this is because there's just sort of, we know that there's sort of a global relationship in that people who have larger lesions tend to be doing worse behaviorally in general. And so it's sort of a little bit of a confound in the sense that we don't just want to say, we don't want to end up with a result where we say that our behavior is driven by people with large lesions, and so we're going to pick up the areas where people have those large lesions, and that's it, right? We want to be able to say something more interesting. So we want to correct for this relationship between total lesion volume and behavioral deficits. And there have been sort of 4 major proposals out there in the literature for how to do this. So there's direct total lesion volume correction, or DTLVC, in which you normalize the lesion status by 1 over the square root of the total lesion volume. And these are all, we've touched on these all last week, so I'm just reiterating quickly. There's regress on lesion, where you basically do a regression of lesion status and total lesion volume. You take the residuals of that regression and you use that in your analysis. So regress on behavior, which is sort of the same idea, but you're regressing behavior and total lesion volume and using those residuals. Or you can do regress on both. And so you regress total lesion volume against lesion status and take those residuals, and you are going to, on the other side of your equation, it's total lesion volume regressed out of behavior. So, Andrew DeMarco, who has put together this toolbox, basically sort of mapped out how these different effects are affecting your outcome. So it's sort of pretty straightforward there. And if you're wondering, the partial correction is there because you're only affecting voxels where there is a lesion, but whenever a voxel is 0, dividing by a number gives you 0. So you don't really correct out voxels where there's no lesion present. Okay, so as it turns out, these corrections all give you very different behaviors. You get sort of the same general picture. And again, this is the data set that Harrison showed you last week. But here you can see the effects of the different corrections on this behavior. And then over here, up on the top right, this is the overlap map. So you can use that as comparison. And basically what you see is that in general, what we observe is DTLVC tends to be sort of the, gives you sort of maps that have the most regions included. So this tends to be the sort of less restrictive correction. Regress on both tends to be the most restrictive correction, and it sort of spans that range in that way. So,
Aaron, it looks visually like regress on behavior is more restrictive than regress on both.
In this analysis, that's possibly what you might be seeing, but in general, what we see is that regress on both tends to be the most restrictive. Okay. This is also kind of an unusual data set in the fact that you get this huge cluster up here and these very large clusters. So it's a slightly unusual data set.
I think these issues also intersect with how many participants you have. So in this case, we have 74, pretty robust data set. But if you're working with 30, 40, then you can start to see some larger differences using these different corrective methods as well.
Great. Okay. Yeah, so there's not really much more we can say about correction for lesion volume other than that there are these alternatives. We still don't know which one is sort of right, but we can definitely sort of, we have some sense about how they affect your data. So that's about the extent of what we know. Excuse me. It's about the extent of what we know so far about this. The other major factor that plays into this is correcting for multiple comparisons. So again, this is at the end of your analysis. When you have your map, what do you do with it to address the fact that you are still sort of calculating statistical power at, or statistical values at your at the voxel level? So of course you can not correct, which is probably not the right thing to do. You can do some kind of voxel level correction like FDR or FWR, but those tend to be really restrictive because you're of course correcting over a large number of voxels. So we again feel like that's probably not the right approach. We definitely recommend doing some kind of cluster size thresholding at the very least. So we want to say that there's a minimum size of continuous voxels that have to exist in order for this to be considered not noise. So that at least gives us some confidence and sort of wipes out all of these little spurious voxels down here that are not very meaningful. We can also do a cluster level correction. And so this is the idea that instead of doing something like FDR or FWER at the voxel level, you can do it at the cluster level. I don't know if there's sort of statistical, I don't know what the statistical rigor is for doing it in that way, but it is a possible option, so we're throwing it out there. And then, of course, there's the idea of doing this cluster size correction, which is what is built into the SVR-LSM analysis script. And again, we feel that this is probably too restrictive, and it's probably not the right approach. The reason is because, again, just sort of to remind you how this works, as you do your permutations, you basically keep a track of all of the cluster sizes that you see in your in each of your random permutations, and then that allows you to sort of build up a distribution of what clusters you might expect to see by chance, so how large they would be expected, and then you compare your data against what you see in this null distribution, and you say, well, if my data cluster, if the clusters that I have are larger than, say, 95% of all the random clusters that I saw previously, then I'm going to keep those. But the problem there is what you're ignoring is sort of the level of significance of those clusters. So what I mean is, for example, in a permutation, you might end up getting a very large cluster where all the voxels in that cluster are sitting at 0.05. And then you might have in your result a very small cluster, but all the voxels in that cluster are sitting at 0.0001. And it's not clear that you should therefore throw out that small cluster just because it is smaller than all of the clusters that you see by chance. So we have some, we think that this is probably not exactly the right approach, but I don't know if there's actually a good agreed upon approach out there. So usually what we do is some combination of thresholding on the size of the cluster and then possibly some correction after that at the cluster level. Okay. So just a little bit more on correcting for multiple comparisons. So what is known is that if you have small sample sizes and you do correct at the voxel level, this tends to be anti-conservative. I don't know if I can give you any kind of intuition for that other than the fact that this is what's been seen by other people. On the other hand, if you correct at the voxel level, it's overly conservative with large sample sizes. I think we can all understand that one. Right. Cluster size thresholding. The disadvantage there is you may not prevent spurious clusters. So you may get a cluster that happens to be larger than whatever threshold you set, but it could be like a little false positive blip in your map. And then, as I mentioned before, very rarely do clusters survive cluster correction. And so what ends up happening is you'll wipe out small clusters which is sort of the whole point of doing SVR-LSM, is that this method is supposed to be better at finding those small clusters that sort of hide in the noise, but now you're basically just wiping them out with your correction method. So you're sort of undoing all the good that you just tried to do. Okay. Some of the other interesting things that we see out there in the literature, or that we've seen in our experience, is that you get some very weird effects when you start to approach what I want to call like edge effects or boundary conditions, so things that are sort of on the extremes. So here's a very strange looking map that we ended up with. And what you can see in this map is that if you look at this particular cluster up here, you notice that it almost looks like it's bounded by a square. And that is something that's really strange, right? So you look at that and you say, is that real? And it turns out that what this effect has arisen from in this particular case is that this test was being run on what we would consider to be relatively low end, so about 30 people. And it turns out that you can go in and find individual subjects who have lesions that happen to kind of cut off right around that point. And as sort of evidence of what's going on here, so this is set so that only voxels with at least 3 people with lesions in that voxel are included in the analysis. So that's what this n greater than 3 is. And as you increase that threshold, you can see that edge effect sort of washing out. And so what this suggests is that when you have low n, even a few subjects can very strongly influence the outcome of your analysis. It turns out, although we don't have an example to show this, but I know Frank has seen in his data that this problem can happen even at higher n. So he had a data set with about 50 people, I believe, and he had one person who was extremely strong behavioral outlier, and that caused a cluster to pop up in his data that wouldn't otherwise be there. Okay.
Now, I mean, one way that helps that is when you have a small sample size, I mean, typically we require 10%, we use a 10% threshold, you might have gone over this, but,
yeah.
You know, if you have a sample size of 50, you need 5 people to have a lesion in the box that's included, but it could be that you need to set that higher, so to avoid, especially if your behavioral data are really skewed. Yeah.
Okay.
So then you may need to just arbitrarily raise that threshold, and that will help you, as you demonstrate here, that will help you get rid of some of those weird boundary effects.
Right. So then that sort of asks, you know, is 10% not the right metric?
Right.
So, yeah. So we don't know for this particular analysis. 10% is what we use a lot with VLSM. It may be that we have to go higher for SVR-LSM. But again, that sort of defeats the whole idea that we're now using this more high-powered technique that should be able to get us more significance and in a more robust fashion. So yeah, I don't know what to do about that. Another kind of interesting boundary effect that we've seen in our data is what we kind of call this edge effect. And this happened, in this case, we had a data set of about 74 participants. And so you can see their overlap map here on the left. And what we got as the outcome of this analysis is basically significance that sort of followed the edge of this distribution. And so you would think, oh, we have lots of subjects here, so we should be able to pick up any interesting effects in these regions where there's more stuff going on. But it turns out that just sort of wiped out all of those areas. And the only things we can see are areas on the edges here. And just as a note, I might have a slide or two later with showing you this, but this particular effect happened because we were using this regress on both restrictive correction for total lesion volume. If you use a less restrictive correction, you actually start to pick up these areas sort of down here where you would sort of anticipate that you should have seen some kind of effect.
And these are one of the findings, I think I remember this, where we started to think that maybe regress on both is actually too strong of a correction.
Yeah. Right. It seems to penalize you when you have where lesion overlap is the highest. So it's giving you the area. So in this case, the map on the right, it's giving you the areas that have the least amount of coverage, or it's penalizing you in areas where you have the most amount of coverage. Is what we see here, and that's typically with a sample like this, it's in infila, lateral to the IFG, and then posterior into the IPL. Right, looks very typical for an NCA. Yeah. Stroke distribution map.
Yep. Yep. Okay. All right. So lots of weird things going on here. Right. So just to sort of summarize, so SVR-LSM is theoretically thought to be an improvement over VLSM, but in practice, it's not without its own set of problems. And so, in one thing in particular is it's possibly not the right tool to use when you have low N. There's probably some minimum number of subjects that you need in order for this to be a reliable technique. But as of now, we haven't sort of systematically probed that to figure out what that N should be.
Just to return to an issue we talked about last week with cross-validation, right? So you want to cross-validate your data, yet with smaller N, you're going to have fewer subjects for training. So it will be difficult to have, if your findings are susceptible to outliers and you have a small N, then it will be difficult to have robust or rigorous training data sets with which to test with the left-out sample, given the small N, right? So a number of considerations to keep in mind. So we always advocate for doing cross-validation, but you need to keep in mind how many subjects you have and if that's an adequate sample given the rigorous approach that we suggest taking using cross-validation and using SVR.
Yep. It also is going to depend upon your subject population. So if you have a lot of people with very small lesions scattered widely throughout the brain, then of course your N is going to need to be higher. If you have a more restricted population where everyone's lesions overlap highly, then you might be able to get away with fewer lesions.
One very basic question that
Yep.
popped into my head. So because it's either regression, essentially, the same assumption holds typically in terms of the distributions of your data.
It's a regression in high dimensional space, which then gets warped down into low dimensional space. So, and it's not a regression in this, well, it's a regression that's being fit by machine learning. So I don't know if all of the assumptions of standard regression apply. I imagine that quite a lot of them do, but I don't want to say because I haven't actually thought about it deeply, whether everything that applies in regression applies here.
Mm-hmm. But it certainly, I think you're raising a really good point. The very fact that you had an outlier, an extreme score that could really skew your results that much suggests that the shape of the distribution is important.
Yeah.
Sure.
Yeah.
I mean, a kind of low tech thing to do, of course, could be to transform your data in the old-fashioned ways before you subject it to, rank it or whatever you want to transform to make the distribution. It might be great in our spare time to play around with what the results are of various skews in the data, in the behavioral data.
Yeah.
Yeah. Yeah, and you can imagine also parametrically modulating the amount of overlap given those skews. So when there's skew and there is a high degree of overlap in the IFG, for example, or in the premotor, I think it was in that.
Right.
How does that border effect change with less skew or with more skew, more skew but less overlap? Or, I think these are important open questions that we just still don't know, given how novel this is. Right.
And it's also it's very hard and non-trivial to actually test all of those options, given that running one variant is going to take you 20 hours.
Although we're working on
Yeah, that's right. But I mean, for most people, it'll be, unless you have access to a cluster, it's going to take a long time. And so, that's why a lot of the papers that have, or the papers that have come out that have sort of been critical of this approach have used very simplistic reductionist kinds of techniques to get at these questions because it's hard to get that kind of computing power, right? So they'll run 1,000 permutations instead of 10,000, and they won't do cross-validation and these kinds of things. And so, as we mentioned before, those have their own problems associated with them, And so you can't just sort of say, oh, everything that I do at low permutation applies at high permutation. So yeah, someone has to rigorously do it, but that person also needs to have access to a very large cluster. And so one thing that we try to do is we try to look for consistency across our analyses. So we will run things a couple of ways and see what sort of holds. And we think that the regions that sort of consistently appear are the ones that are more reliable. But of course, as many of you know from your basic stats, if you run the same test multiple times, you start to invalidate your statistics. So that's problematic also. But it gives us a little bit of confidence, at least, that we're looking at something that isn't just purely false positives and noise. So basically, the whole point of this is you really have to know your data well. You have to know what your lesions look like in your individual subjects. You have to know what the overlap map looks like, and you have to know what your behavior looks like. And if you have a good idea about all of those things, then when you get your results, you should be able to say, this makes sense, or this doesn't make sense, or I think that my method was correcting too harshly in this way or not harshly enough. But you really have to have a good sense of what's going into the equations before you are able to interpret what comes out of it. Okay, so that's about all I want to say about SVR-LSM. So it's this approach, as we mentioned, that's this nice multivariate approach, but it has problems. So is there anything else out there? That's the question, right? And it turns out that there is one other method out there that has been proposed, and it's this method called SCAN. And it's a multivariate analysis as well. And the sort of advantage of it, I guess, is that it does not compute significance at the voxel level. So I'll explain how this works. And it's a little bit hard to grasp. So if you have questions, stop me.
SVR is just so easy.
yeah, we were talking about this before, and we think it's because SVR is sort of like a nice next step after VLSM, and SCAN relies on a completely different discipline of math, which has been around since the 30s, but most of us don't think about it because it's not really in our wheelhouse. So, all right, so SCAN is run in R. So for those of you who are anti-MATLAB and like R, you will probably like this approach better. But it is the less used approach, I think, largely because people have a hard time wrapping their heads around what's going on. So let me try to give you some intuition or sense about how this works. So we're going to start out talking about canonical correlation analysis, which is the mathematical basis for SCAN. So let's imagine that you have two sets of variables. Okay, so these are not like, I'm not talking about like two sets of, or I'm not talking about two like subjects, for example, but two sets of variables that you're interested in thinking about. So these variables could be two behavioral scores or two voxels in your map or something, okay? And so imagine that each of these variables has sort of two things. So like I said, like maybe this is voxel 1 and voxel 2, and this is like behavior 1 and behavior 2, however you want to think about it. But basically, you can imagine that these two sets of variables form some plane in space, right? So what I want to do is I want to be able to say something about how similar the relationships between these sets of variables are. And so what I'm going to do is I'm going to say construct two weighting vectors, A and B, such that they basically are just linear combinations of all of my variables, okay? And they don't have to be like ones and zeros, they can be fractional weights. And I'm going to define A and B such that what they turn out to do is they maximize the correlation between the sort of weighted outcomes of my variables of interest. Okay, so this is a correlation, not a regression. So that's one key difference to keep in mind. You're not talking about behavior predicting, you're not talking about voxels predicting behavior or something like that. You're really talking about a bidirectional, like, how are these two things correlated with each other? And so how this sort of plays out when you start talking about imaging analysis is sort of as follows. Does that sort of make sense to people? Okay. So practically what you're doing in SCAN is you have a set of voxels that you're interested in, right? So these are my sort of variables of interest in this space, and I happen to have these variables sampled across numerous subjects. And then in this case, I have a single variable of interest, which is my behavior. So that's why things get a little hard, is because canonical correlation analysis is meant to deal with multivariate, two sets of multivariate things, and here we're sort of dropping down into where one of these is a univariate set of things. But in any case, I can imagine that, again, I'm going to assign some weighting vectors to these sets of variables. And I want to construct these weighting vectors such that when I project my data into the space defined by these weights, that I have a maximal correlation between my two spaces, right? So another way to think about this is that you're basically constructing a basis set for each of these spaces separately, and you're going to construct that set basis in a way that when you project your data into that basis, the projections in each space are maximally correlated with each other. Okay, so on the behavior side, we can sort of wipe out all of that because there's only one thing, so it has to be weighted by 1, hopefully, and not 0. And then, so the question is, how do you deal with the weights on the other side of the equation? So this is where the sparse term in this analysis comes in. So we're going to require that our weighting vector be sparse, meaning that most of the weights in that vector should be 0. Okay. I'm going to talk on the next slide about how we actually figure out what that sparseness value should be. But just based on how you set the value, you'll get more or less zeros in your weighting vector. And then there's also one other additional thing thrown in here, which is that, yes, you could have sort of this vector of weights, but if you have a single voxel isolated by itself, we know that that's really meaningless practically speaking. And so what we're going to do is find all of those isolated voxels. It's like find all the voxels that cluster at where the cluster size is less than some threshold, and we set all those back to 0. Okay. So we have inherently built into this method a cluster size threshold, which is applied as you're calculating the weights. Okay. So everyone with me so far? Okay. So the question is, how do you figure out what that sparsity value should be? So just taking a step back, if we take all those weights, rearrange them into our map, those become sort of like the feature weights or the beta values that we've been talking about in SVR-LSM. So they basically, whenever there's a non-zero weight, that is an area that is sort of significantly correlated with our behavior. In this case, larger weights mean stronger voxel behavior relationships, and we do not get a voxel level statistical value. And again, the extent of the map depends on the sparseness value. So how do we determine sparseness? Okay, so the way that it works in SCAN is that we actually use an iterative cross-validation approach. So what we say is we want to find the sparseness value the minimum sparseness value, meaning the most sparse map that we can have, that still maintains our prediction accuracy and cross-validation. So we say, so of course, as the map becomes more and more sparse, what's going to happen is that if you had like a strange behavioral outlier, that's going to drive a peak in your map because you're sort of overfitting your map to the weird peaks in your behavior. And so to avoid that kind of thing, we run cross-validation where we take out a test set and a training set, we calculate these weights on our training set, and then we check how well that predicts what's going on in our test set. And we want to make sure that our prediction accuracy is good. Okay. So there's sort of an iterative approach built into this analysis that steps through different sparseness values and figures out what's the smallest sparseness that still gives you reliable cross-validation. There's a penalty built in for larger sparseness values, so that sort of drives your gradient towards a smaller sparseness. And it turns out that sparseness is not quite analogous to simply thresholding a beta map, like what we were talking about in SVR-LSM. It's because the sparseness value affects sort of how you calculate the weights, since you set the sparseness and then calculate the weights, and then and so that sort of dictates how those weights actually get set. Okay, and because we're doing cross-validation, we can come up with a p-value, which tells us how sort of significant or successful our cross-validation was. And so what we end up with is one p-value for the entire map. So now we have one significance value associated with an entire map. We don't have to worry about significance values at the voxel level. And the p-value just tells us, is this map interpretable or is it just random noise? If your p-value happens to come out to be non-significant, the code, unfortunately, so we've spoken to the person who wrote the code. He says that he deliberately takes whatever outcome map was the best and then wipes it out. And so he gives you back a blank map if you end up with no significance, which is really annoying. But he says it's because he doesn't want people to try to interpret maps that are non-significant. Apparently, he has not heard about pilot data for grants. But just to sort of summarize, so this whole approach you can think of as being the complete opposite of what happens in SVR-LSM. So is it good? Well, okay, so when you run the analysis, this is basically what you get out, which is a lot of gibberish. You can see down here, it's sort of checking all these sparseness values. In this case, this is a data set that we provided last week. It actually turns out that it gives you a null result. So it would have given us a blank map, except we then ran it again and asked for it at a higher p-value threshold so that it actually gave us something back. And that's what it gives us back. And just to remind you, that's what we got back from sort of the least harsh correction for total lesion volume method there. So what you can see is that SCAN actually gives you more or comparable coverage to what you would get from the least harsh correction methods you can apply in SVR-LSM. And this is something that actually has been touted with this method, is that it gives you more stuff back. But we don't know if that's a good thing or not.
But you have to ask for an increased p-value, right?
In this particular data set, but across data sets that we run, even when we don't change the p-value, so we ask for p-value at 0.05, and all the default parameters, it tends to give you back more stuff.
So is it better for small n?
That is a good question. Yeah. we haven't tested this method well enough to know how it behaves as you vary the N. Again, Harrison's the one who has run most of these analyses, so he would probably be able to come up with some sense. I do know that at small N, we have a really hard time getting anything out of here that turns out to be significant. And this is probably, again, due to the fact that you're relying on cross-validation to get this p-value out. And so if you have small N, you end up dividing your sample into really small numbers, and then you end up sort of inherently overfitting your data, which makes your cross-validation bad, which means you get nothing out at the end. So there is probably some minimum N, again, that you need. We haven't tested this method enough to know what that is. And it, again, probably depends upon like your lesion distribution and all of those fun things.
Just one comment that springs to mind is that these are all fairly new methods, right? Not new techniques in terms of them existing, but the application to lesion-symptom mapping. And back in 2 years ago now, in 2018, there was a special edition in Neuropsychologia of lesion-symptom mapping and, progress, pitfalls, new techniques, corrective methods that I suggest everyone check out, or you can contact me and let me know, and I can share a link with you to those PDFs, because it is a collection of 15 to 20 authors, all of whom have been in the field now since the inception of lesion-symptom mapping, so about 17 years, and have been doing cognitive neuropsychology now even longer. So there's their opinions of their techniques, what they've been doing, what the issues are, and where they see the field moving going forward. So, as we're saying here, these are issues we're still trying to understand and tackle with our data. Other people are focusing on this as well, and so I just wanted to refer everyone to that special edition because there is some good content there that talks about how to move forward in rigorous and careful ways.
Yeah, and a lot of the stuff that we apply here happens to be on real data because we're actually wanting to know what the outcomes are for various experiments that we're running. But in those papers that Frank mentioned, they also do these analyses on synthetic data where they know what the outcomes should be. So you can see how good they are at recovering sort of the ground truth. Okay, so as I mentioned, if you compare SCAN to other methods, you often get similar or more significant numbers of voxels. So here's, again, this is the large map of 74 subjects I showed you earlier. If you run VLSM, you get sort of concentrations of voxels down here. If you run SVR, you get this edge effect, but you get those concentrations of voxels sort of up here at the top of the map. And then in SCAN, you get sort of a much more dense map in general, although it does tend to concentrate down here again. So yeah, it's sort of an open question. How do we know that more is better? So SCAN has by default, there's no total lesion volume correction. You can add one in if you want, but it doesn't inherently have one. You can set the flags to add them in. There's no voxel level or cluster level multiple comparisons correction and you shouldn't need one in this case because it is purely a multivariate method. But that again means that you have no way to sort of take areas out of your map after the fact. And so you just sort of have to assume that everything that's in there is real. And I don't know if that's a good assumption. And then there is a built-in minimum cluster size, but we can also sort of do a post-hoc more rigorous cluster size correction, which is probably not going to be equivalent to setting that cluster size correction in the method to that same value. So these are going to have sort of inherently different effects on your outcomes. Okay, so I think that's it for me. And I'm going to turn it over to Frank, who's going to talk about an interesting extension of sort of these approaches and sort of getting away from the whole lesion, well, sort of.
Connectivity.
Yeah.
Yeah. Cool. Okay. So, I just wanted to take a step back before I get into it and just, I like this figure because it outlines numerous forms of connectivity in the field. So in my PhD, I did a lot of functional connectivity, so that's with functional MRI data, and that is looking at correlations in the bold signal, right, across different regions in the brain, and looking at synchrony in the bold response across different regions. That gives you an R value, a correlation value. That's what most people refer to when they refer to functional connectivity. Structural connectivity, on the left here, takes various types. I mean, of course, we've heard about diffusion tensor imaging, and that allows you, using diffusion weighted imaging, allows you to map out white matter tracks, fiber tracks, okay? Various other methods by which one can do this, looking at autopsy, postmortem studies, et cetera. So there's a lot of convergence in how individuals study brain structure and function, studying white matter tracks and fibers on that front, studying functional connectivity, looking for correspondence, et cetera. Okay, and so with my background in doing connectivity, I've been interested in using SVR, support vector regression, to inspect disconnection in patients, right? So where there are regions that are disconnected, and using the same kind of multivariate approach to be able to understand, instead of just looking at two individual regions, you can look at a whole connectome-wide amount of disconnection, and you can look and use SVR to be able to pull out those disconnection patterns, the edges, so the disconnection between regions that are most predictive of your behavior, like we've talked about with lesion symptom mapping, okay? So in that case, it's with voxels. In this case, we're going to talk about a connectome, okay? And so what do I mean by connectome? Well, the approach typically looks something like this, where you so we talked about this in session 1 with Austin, where you have your participant's brain, their T1, and you draw in their lesion, okay? What you then do is, with various types of warping techniques, we use some of these as well. You can separate out gray matter from white matter, right? And you can see that some of the tissue is not there. That represents where the lesion is, okay? And what this allows you to do is it allows you to derive, using the separation of the gray and white matter from lesion, it allows you to take these kinds of masks here and apply them to your diffusion data. So then you can look at and inspect your white matter. Okay, so this is usually a FA map, fractional anisotropy. That's what you'll see here. And then what that allows you to do is, in your patient of interest, you can remove out the lesion and study the residual white matter connectivity. As you can see represented here, you can inspect the likelihood that any regions are connected after having removed out corruption in the signal from the stroke lesion. And then you can typically represent it in terms of these heat maps, where, let's imagine you have 100 regions in an atlas. You'll have warped your stroke participant's brain to that atlas. You'll have then warped their structural images to that atlas, so that you can look at region by region connectivity or disconnection in patients. And you can start to enter these types of data sets into SVR algorithms, right? So SVR, what we've shown is that you have a whole brain of data. You turn it into a vector, you turn it into a column, and then each participant has a column of data, and then there's a unique column of behavior, and the input of the data sets and the behavior is what goes into the SVR analysis. In terms of connectome lesion symptom mapping, you can use any kind of matrix of connectivity data that you have. So in this case, you can use probabilistic tractography as one form of diffusion tensor imaging. You can use resting state functional connectivity. It really is quite flexible. What I'm going to talk about from some of the work I've done more recently is using structural connectivity or disconnection on the basis of stroke lesions, okay? So that would is represented here in this approach. And I suggest, if you all are interested in it, to check out this paper. This is from a group in South Carolina. They've done a lot of, Julius Fridrikson's group, they've done a lot of good work making progress recently, and it inspired some of my interests reading their papers a few years ago in terms of how to apply multivariate approaches to connectivity data. Okay, and I'm happy to send you some of those papers out to you folks if you want. Just let me know. So what you do, so this is a pipeline, right? And you can apply it to each stroke patient. So I've shown this image before. Here's a group of participants who we have lesions drawn and for which we can also measure disconnection in their brains. Okay, And so the point being with this approach especially is that this approach is built to study lesions that are, so as Aaron said, big lesions have large disruptive effects. Patients tend to be overall impaired across the board. But actually small lesions can have large disruptive effects if they're in close proximity to major white matter tracts. So take, for instance, this patient with a small left inferior frontal gyrus lesion, okay? So this is typically the output that we get after having warped this to MNI space, okay? You can represent this lesion in the surface space like so, and then what you can start to see is with the approach that we get, that you can appreciate that even small lesions have large disruptive patterns, right, given their proximity to major white matter tracts. So in this case, this patient who has a frontal lesion actually has disconnection that cascades all the way posterior into pre and post central gyri, okay? So what we want to be able to do is to use this data set, right, much like how we have lesions that are voxels that are lesioned or not. Now we have a continuous measure of the degree to which two regions are disconnected, and we can enter that information into the SVR analysis, okay? Here is just a snapshot of finding that is not too dissimilar from what we've been looking at before. This is an analysis of tool use performance, okay? And so you typically find two large clusters, one that includes supramarginal gyrus that also extends into angular gyrus and even into some portions of the spherotemporal gyrus, and a second cluster in the inferior frontal gyrus that extends into middle frontal gyrus, including ventral premotor. I wasn't planning to talk much about this finding in and of itself, but what I want to show you is actually that what we can start to do is take SVR-LSM, what I'm showing you here, and load up these same data, okay, into a surface representation like so, okay, and we can compute the same analysis of tool use performance of our behavior with the Connectome lesion symptom mapping. And so now we can look at correspondence between where we find disconnection in the brain that predicts worse performance in tool use in this context, and where the voxel lesion symptom mapping results are in red, okay? So I just trying to help you transition from slide to slide. So what I'm going to show you now is that disconnection pattern in orange. And so what you can appreciate is there's correspondence between the lesion sites in red and the disconnection patterns in orange, and that we get disconnection between parietal cortex that extends into frontal regions, okay, but also into inferior parts of the temporal lobe. And that's interesting on the basis as it relates to theories of object and knowledge and action knowledge in the brain, and how these different types of information are integrated in our ability to pick up objects and use them, okay? And so what you can start to appreciate is the full sort of cascade or the disconnection pattern that we get at the group level that we wouldn't get with doing voxel lesion symptom mapping alone, right? So these provide complementary sources of information about where lesions and disconnection patterns are associated with poor performance in your task. Okay, so as I mentioned, what I've done in the last few months is to use the strengths of lesion symptom mapping and SVR, using it with the Connectome-based data and looking at correspondence across the two. Obviously, these are independent data sets, but they converge on similar brain regions, similar nodes in these networks that we're studying. Okay, and so sorry for the it looks like the formatting is a bit off, but what you can appreciate is then you can represent the cumulative amount of disconnection or edge weight disconnection. So this is the likelihood that any two areas are disconnected, much like how we talked about our beta values in the second session. These have been interpreted such that you get your beta values after running the SVR. You then do permutation testing, right? And then you z-score those beta values with respect to those, with respect to the values that you would that you identify when you do the permutation. We've also used some novel graph theoretic techniques that are really suited to studying networks, where you can say, here are all of the significant edges that are disconnected in association with the behavioral task, and we know that they're stronger than what we would observe in the permutation. And what these graph theoretic measures can do is actually try to find sparseness in the data, as Aaron was mentioning, can try to find where where disconnection that is not just local to any one edge, but where the cumulative amount of disconnection in the network in the aggregate accounts for behavior over and above any one edge that may have a strong disconnection pattern. So what these types of graph theoretic measures are trying to do is to find sort of a posture or think of it like a principal component analysis, where it's trying to find a single component that identifies the most amount of disconnection in your network. So what we feed these graph theoretic algorithms are the disconnection patterns that have already survived permutation level analysis as a way of sort of doing a kind of clustering like we do with the voxel data. You can apply that kind of approach to find the most amount of disconnection that's in different parts of the network that is significant, and as I mentioned, that is in distinct regions, okay? And then you can use other types of methods in graph theory to quantify just cumulative amount of disconnection at the node level, right? So now you can color code these regions on the basis of their cumulative amount of disconnection that you derive from the graph theoretic analysis, where you try to find a subgraph or a subnetwork of maximal disconnection. Okay, so this is just to give you a flavor of the types of extensions you can apply after having done the SVR approach. I was just planning to talk about this data set as an example. As I mentioned, I'm happy to talk in more detail about issues related to connectome symptom mapping and voxel symptom mapping, but the general flavor that we want to give you guys is that the approach is quite flexible. You can use numerous types of data in the SVR analysis. So you can also apply resting state functional connectivity data. In this case, I'm showing you structural disconnection, but you can also look at functional disconnection as well. Many individuals do that. We can apply that with some of the functional imaging data that are collected here. So that's just to give you a general sense of the extensions of this approach. Cool.
Presumably, you can also drop this into a scan, although we've never tried it.
Yeah, presumably. That's a good, yeah. I don't know what that would look like, but I haven't tried it, but yeah, it's a good point.
Yeah, internet general questions.
You guys tried using both techniques, like with disconnection and just lesion and voxel?
Sorry, say that again?
Have you tried like voxel level lesion symptom mapping?
In tandem?
In conjunction with...
Oh, I see. Not quite. So it's a bit weird. I mean, in terms of like, in terms of applying the data that you give the SVR algorithm, it would be, I don't know how the SVR algorithm would handle having two just fundamentally different data sets going into it. I don't think it would work.
Not comparable, really.
Well, what I've done, yeah, but what I've done actually is that prior to entering the disconnection data into the SVR algorithm, you can regress out. So as we've talked about regressing lesion volume on voxels prior to running SVR-LSM, you can regress out edge to edge, so node to node disconnection values. That has a strength. So imagine you have 50 participants. They have 50 connectivity values there. Then you have a second vector of the lesion size. You can regress out lesion size from the disconnection data, work with the residual disconnection data, and then enter, much like how we do with lesion symptom mapping. So we work with the residual voxel data after having regressed out total lesion volume. That's what I've done here. You can also, it's, you know, but you can include other variables of interest. So if you know, for instance, from your voxel lesion symptom mapping analysis that we identify parietal lobe, frontal lobe, et cetera, different regions of interest, you can compute total amount of damage to those areas for each person and regress that out as well, like you would regress total lesion volume. So it's incredibly flexible. All that you need to give it is a data set of values that's the same size for all of your participants. So in this case, I have a matrix of 64 regions. So every participant has a 64 by 64 that gets turned into a vector, and that vector can be processed in numerous ways prior to entering it into the SVR approach. What that gives you, so 64 by 64 gets turned into a 2016 by 1 column for each person. The output of the analysis, once you do the SVR, is beta weights, feature weights for each edge. So a a vector of feature weights. You then bring that back into 64 by 64, much like how we would talk about you get a whole brain map of raw beta weights from your voxel lesion symptom mapping, right? Then you just do more permutation testing like we do with these other approaches. So it's the same pipeline. What I wanted to do is keep it close with doing connectome symptom mapping and voxel symptom mapping using the same code, the same pipeline. The only thing that changes are the data that you give it to learn the relation between damage in the brain, whether it's voxel level loss or connectome level loss, and behavior. So the only thing that changes are the inputs, the data. The behavior stays the same participants, same lesion size. So then you can start to look at correspondence, and you can also start to look at differences across these two types of analyses. Yeah, I mean, but at the same time, it's very simple. You know, it's the same. It's not simple, but it's. I mean, the analyses aren't simple, but the idea is you try to keep as much constant, right, and change just the input that you give the algorithms to learn the relation between the data and the outcomes. And in theory, you should see correspondence with your voxel data and your connectome data.
Yeah, so this, in a way, gives you a sanity check on the maps you get out of your voxel level maps. Because now you can say, well, does it make sense in conjunction with the disconnection maps that I'm now seeing? Unfortunately, I don't have it here, but in the same group of patients, they did right hand grip strength as a measurement of hemiparesis, you know, so that localizes. So in stroke, grip strength weakness localizes well to damage in the motor system and cortical spinal tract. So what I did as a control was the same analysis I'm showing you here, but with right hand grip strength, controlling for left hand. So what I want to see is abnormally weak right hand grip strength, right? And where does that localize? So you can look at individuals who are abnormally weak with the right hand compared to the left. That localizes to the cortical motor system, but also in subcortical regions and in and around the cortical spinal tract. And when you do the same approach with the connectome lesion symptom mapping, you see similar disconnection patterns. So I think about it as a way of also doing a sanity check where it's like, okay, here are the lesion sites I get in my SVR-LSM, and here are the disconnection patterns in the SVR-LSM. So there is correspondence, for sure.
So how robust is this to sort of non-focal lesions if you're dealing with like a degenerative, like you're doing like MS lesions or something like that, because they're sort of small and dispersed. Would you adjust your cluster threshold, or?
It's a great question. I'm thinking, as I mentioned earlier, the special edition in neuropsychology, is mostly in stroke, right and left hemisphere stroke. I don't know if it's been looked at in MS, but thinking about voxel.
Any degenerative, yeah.
Yeah. I mean, degenerative disease is difficult because you're talking about, yeah, I mean, it's hard to sort of draw the lesion map in the first place, I think.
Yeah.
Yeah, that's why I thought it was.
I mean, I think, take a step back. Sorry. I was going to say, taking a step back, I think that's why many scientists, clinicians have focused on resting connectivity, because it's so easy to have a patient go in the scanner for 10 minutes and you can quantify, a reduction in resting connectivity. Presumably you could do the same with structural connectivity. And actually this approach might be better suited in individuals who don't have a sort of frank lesion in the same way that a stroke or a tumor patient does. Yet they may have, more subtle disconnection patterns or lack of structural connectivity that may be.
Yeah, usually you would do like DTI.
Yeah, that's right. Yeah. So this approach, as I've shown you, the second approach, doing connectome-wide loss, may be more appropriate in that way. What we found though in the SVR-LSM is that, with some of these border or these edge effects, if you have very if your behavioral findings don't localize well, if there isn't a precedent for a certain area being associated with a certain deficit in behavior, then you'll almost get penalized in a way, as we talked about before. You'll get, sometimes it will give you these edges, and so I think one just needs to be careful and know the distributions and know if you have adequate coverage, voxel level lesion coverage, before doing the SVR approach. Cool.
Well, thanks everyone for coming to and bearing with us for 3 weeks. Hopefully you found it useful. As you mentioned, if you have questions, you can always contact us after the fact. You can also, I know locally we're planning to save all of these sessions as recorded video, so if you want to watch them again and sort of slow everything down, you can do that.
Yeah.
But otherwise, yeah. So if you are planning to use these techniques, good luck. Make sure you know your data well. Don't just sort of throw everything in and assume that it's going to magically give you the outcome you want at the end. And if you have questions, of course, just come and find us, and we'll be happy to help you.
Thank you.